Hi everyone. I want to help you with the reverse chain rule because I know a lot of students do not like the reverse chain rule. And one of the reasons being that when you learn this in school, the way you're told to do it is to look at the integral and make a guess. And then you have to correct your guess, right? But it can feel quite difficult to know what to do when you're just told, well, just look at it and have a go, right? So I want to show you a different way to do this, which will work every single time. Now, any reverse chain rule question, this method will work on. And also, it's more of a set method that you can actually follow and take the steps. And a lot of you, I know, would really like to have a method to follow. And just very quick disclaimer, like nothing wrong with reverse chain rule, like it's really good. I just think you have to be very good at differentiation, like very good, to be able to do it effectively. I think for some of the questions, if you're not able to differentiate something like, let's go 6 tan cubed x squared plus 7, if you can't differentiate something like this very quickly in your head, then you might struggle with the reverse chain rule. If you're curious, the answer would be 36x tan squared that times x squared that. Right, so if you couldn't do that quickly, this is the video for you. Okay, so what's my method? My method is, instead of doing a reverse chain rule, you can do it with a u-substitution. Okay, any reverse chain rule, you can do a u-substitution. You just have to know what substitution to make. And that's the only difficult part. Once you've got the substitution, it's very quick. Right? If I told you to do this question with u equals sine x, you'll just be able to go, I hope. Right? Substitution is quite a lot simpler than doing reverse chain rule. So how do you know what substitution to make? Well, what you do, you're going to look at your function, and you need to search inside the integral symbol, you need to search for a function, which we're going to call u, and the derivative. Okay, that's going to be du by dx. So inside this integral, I can see a function of sine. Right, remember that sine to the 4 just means sine of x all to the power of 4. And I like my function, remember we call it u, I like it being sine because the derivative of sine is cos and the derivative is also here. Okay, so the derivative has to be there as well. The only rules here is the derivative, so in this case the cos, it has to be multiplied inside the integral symbol. So, you know, if this was something like 1 over cos x or sine x divided by cos x, right, that doesn't work because the cos is not multiplied. If it was cos x plus, right, this would not work, it's not multiplied. If it was e to the cos x, right, this would not be any good. The derivative has to just be there, simply multiplied. And that's the only rule. You don't even have to have, like, I haven't even mentioned the power of 4 yet. That doesn't even matter. As long as the derivative of the function is simply there, multiplied, this should work. Okay, so let's work it through. So u is sine x. You need to do the derivative. This is just how I do substitution. So nothing new here if you know how to do integration by substitution. And when you substitute in, just make sure on that kind of first line, you're just doing the obvious stuff. So cos x, I can't write it, very obviously in terms of u. So obviously I could say it's like the square root of 1 minus u squared, but don't bother with that yet. And I forgot to write here, you do du equals cos x dx, so you can replace dx, right? You want to be able to write everything with the x in terms of the u. Okay, so cos x is just cos x. Sine x is u, so this whole thing becomes u to the 4. And then dx is du over cos x. Okay, and the point is, what's happened is the cos x has cancelled off. And I just have the integral of u to the 4 du, which is u to the 5 over 5 plus c. And then just remember to put it back in terms of u. So that's sine to the 5x over 5 plus c. And we're done. Okay? So I search for a function whose derivative is multiplied, and I just made that substitution, u being that function. Okay, so next one here. I need to look inside here, look for a function and its derivative. So something like e to the 3x squared plus 7 would not work without being u, because the derivative of this would be quite complicated, quite a long thing. It's usually going to be a nice simple substitution to make. Actually, the 3x squared minus 7, if you differentiate that, you get 6x. You might be thinking, oh, that's not quite it either, right? If this is a 6x, that'd be good. If you're off just by being multiplied by a constant, you're fine. It's still going to work. So this could be a 14, this could be a -4. It doesn't have to be exactly right, because if u was 3x squared minus 7, the derivative is just 6x. It's only off from 4x by multiplying by 3 over 2, so that's fine. So we can go with this. So let's write everything in terms of u. So dx is going to be du over 6x. And then we just go for it. So 4x is still just 4x. I can't make that nice and obvious. That's fine. This thing becomes e to the u. And instead of dx, I'm going to have du over 6x. And again, what's going to happen, this is going to be a common theme, we get the cancellation. It doesn't quite fully cancel because the 6 is not equal to the 4. But that doesn't matter, right? We can deal with that. It's 2/3 e to the u du. And this actually just integrates to itself, doesn't it? That's just 2/3 e to the u plus c. Put it back in terms of x. That's 2/3 e to the, what was x? Sorry, what was u? 3x squared minus 7. That's it. What I really like about this method is I didn't have to worry about the constant. So with the reverse chain rule, you're very often, you make a guess, it's not quite right, you have to adjust. This 2/3 would cause a bit of issues. It all just comes out by itself within the substitution. So it kind of does all the work for you. I really like it. Number 3. Give me a second to have a look at this one. It's not immediately obvious what my u should be. Okay, you need a function and its derivative. So you might first think to do tan. But if u was tan, the derivative of tan is sec squared x. So this 4 is not 2, right? That was a 2. U equals tan would be great, because then I multiply by its derivative. That's not quite it. Okay. Well, try sec. Why not, right? If u was sec x, again, don't make this like sec to the 4. Sorry, it should be sec 2x, shouldn't it? It shouldn't be a complicated substitution. As soon as you do something like this, differentiating this is already using the chain rule. It's already quite a lot. Okay. The derivative of sec, you are given this, is sec x tan x. So this would be sec 2x tan 2x. And then by the chain rule, I'm going to have to multiply by a 2 there. Sec 2x tan 2x. Well, that is here, right? I didn't remember my dx. That is kind of here. If I rewrite, if I take this sec to the 4 and split it up a bit, if I make that sec 2x tan 2x, and then I've still got a sec cubed. Now hopefully you can see that the derivative of sec 2x tan 2x is right there. Okay? You don't actually even have to rewrite it like this. It's just I've just done this to show you that the derivative really is there. Okay, so let's just go from the beginning now that I've convinced you that this is the correct thing to do for u. You would say, okay, well, u is sec 2x, du by dx, I've already written all this, 2 sec 2x tan 2x. So dx is going to be du over all that. Okay, so I rewrite, right? Instead of tan 2x, well, I can't rewrite it nicely, so I'll just keep it tan 2x for now. At this point, hopefully you can see it's going to cancel off when I divide. This sec to the 4, now I'm going to divide by sec tan. So I'm going to do what I did earlier. I'm going to keep one of those sec 2x's as a sec, so it can cancel off. And the other sec cubed can now become u cubed. And instead of dx, I'm going to have du over 2 sec 2x tan 2x. At this point, hopefully you can see the pattern, and once you can start doing this in your head, you're just doing the reverse chain rule. It's just a bit more explicit. Okay, so I get some cancellation here, the tan sec and the tan sec. I still have this 2. Don't forget about the 2. This is going to be, so that 2 is in the denominator, so 1 over 2 u cubed du, which is just u to the 4 over 8 plus c, so sec to the 4 2x over 8 plus c. Final answer. Again, that 2 here, which might have been tricky with the reverse chain rule, it's just been dealt with automatically. I'm going to put something on the screen in a minute for you to try yourself. One more. I want to do one more. Again, we're looking for a function u and its derivative, and the derivative has to be multiplied. So, u being sine wouldn't be great, because then the derivative is all the way down here in the denominator. I sort of want this piece to be my derivative. So what could you be? You could be a few things. You could be just cos 3x. It could be 3 cos 3x. It could be 4 plus 3 cos 3x. They actually all would work, and it'd all be just as simple as each other. I'm going to choose this one. Point being, the derivative, which I need to be multiplied, well, the derivative is, doing the chain rule, negative 9 sine 3x. So again, it's only off by that. That negative 9 is not a 5, but that's not a problem. We'll just deal with that. The fact that it's sine, and hopefully you've seen the pattern by now, we're going to divide by this derivative. That's always what happens, right? When we rearrange for dx, you always end up dividing by that derivative. And this is why this substitution is always going to work, because you'll divide through by that thing, and you're just left with something more simple. So we still, do the whole thing. It's just a method at this point. Once I know u, it's very straightforward. This is 5 sine 3x. This whole denominator was u, and instead of dx, I had du over negative 9 sine 3x. So the cancellation, that's negative 5 over 9, 1 over u du, which is negative 5 over 9 ln absolute value u plus c, or negative 5 over 9 ln absolute value 4 plus cos, sorry, 4 plus 3 cos 3x plus c. And it works. Okay, so as long as you can spot somewhere in the expression a function and its derivative, and as long as that derivative has been multiplied, so that when you divide it will cancel out, just setting u to be that function will always work. Again, look at this example. U is 3x squared minus 7, so the derivative is 6x, so I divide by 6x, and that will very nicely cancel off with this 4x, and we're left with something that's just e to the u. And, I think for a lot of students this could be really helpful. So if you like the look of this, I want you to try it yourselves. I've got 3 examples down here, A, B, and C. You can try them all at once, or you can try them one at a time. I'm going to reveal the answer one by one. So if you want to just try the first one, pause the video, and I'm going to reveal the answer in 3 seconds. Okay, answer for the first one. So what you should have chosen for your u, u should have been sine x. It doesn't have to be complicated, nice and simple. Okay? And if u is sine x, the derivative is cos x, and that will divide. And what you're going to get should be 1/4 sine to the 4x plus c. Okay? That's your final answer. B, I'll give you a few seconds, pause the video, give it a go. Okay, B, now you want a function, its derivative. The function is tan, because the derivative of tan is sec squared, and that's right here. And that's also multiplied, so it's going to work nice and easy. So you should get 2 e to the tan x plus c. Okay, that will work. Try this last one. The function and its derivative. Okay, the very last one, your choice for u was 3x squared plus 24x. Okay. Reason is, the derivative here, if you do it, is 6x plus 24. And that is exactly off from this by a multiple of 3. Okay, so if my question was 2x plus 9, this is very difficult. This is, I think, further maths only for this, right? Because it's a 2x plus 8, it's very nicely an exact derivative. This substitution will work. You'll divide through by this, and you'll just get a factor of 3, or 1 over 3. And your final answer should be, it's going to take me a second now. I'm going to write this, and then I'm going to double check it. I think it should be 2/3 square root of 3x squared plus 24x. Let's see, I'm going to double check by differentiating. So what I would take the 2/3, I get the power of 1/2. I'd also multiply by the inner derivative, 6x plus 24, and then 1 over that square root. And then this gives me 1/3, and yeah, that all works. Okay, this is correct. I just want to point out, this method not only covers the reverse chain rule, but also covers, for example, 4 over here. This was one of those f dash over f situations, which is natural log of absolute value of f. Right? This method will also cover this situation, right? If your u is your f, your denominator, and then you get the f dash in the numerator and it divides out, it's the same exact thing. So if you found this helpful, please share it with any classmates who are also struggling with the reverse chain rule, and try and explain the method to them yourself. That's going to really help you get very good at it if you explain it to other people. You can also show them this video for a full explanation, and yeah, just share it if it's helpful. Let other people know, and good luck with your revising.